Okay, so let's add a little bit of details in terms of how precipitation response to global warming can be understood. Basically, there are some ideas about energetics, how the radiative perturbation at the top of the atmosphere or perturbation to the amount absorbed in the atmosphere can produce a precipitation response. Essentially, global warming is where we are increasing greenhouse gases and we are changing the radiative balance at the top of the atmosphere. And of course, you know that the main impact of global warming or increased greenhouse effect is that the surface gets warmer. So the radiative forcing at the surface and the top of the atmosphere with the energy released by precipitation changes, condensation, heating is going to be key in determining energetic constraints of precipitation response. Typically, you can do it easily at the global scale, but there are some ideas on how the approach can also be applied at regional scales, which is always tricky, right? So just look at the energy equation here. The L is the latent heat of condensation and P is precipitation, so you can get the energy released there. This is the net long wave minus short wave, so the net energy that's absorbed, and this is the sensible heat be coming into the atmosphere from the surface, and HT is the energy transport out of the column that you are looking at, and this is the internal change in the energy. And this is the water balance where you're looking at precipitation equals evaporation minus the transport minus the change in the storage term. You can integrate this over the globe, and HT would go to 0 because there's no transport out of the column if you integrate it over the whole globe. Sensible heat is typically neglected, which is not always a good idea, and the internal change is also considered small, in which case you can get the perturbation to precipitation as approximately equal to, I don't know, my cursor is not working so well here, equal to the net radiative forcing. Okay, so the main idea then is in this simplified form. There are fast adjustments to radiative forcings, such that direct heating by greenhouse gases, for example, suppresses precipitation through increased atmospheric stability or reduced tropical circulation. So you can look up these papers which look at the robust responses to radiative forcings or greenhouse gas forcing, and through coupled processes reduce evaporation, thereby effectively transferring the heat from the atmosphere to the heat sink of the vast oceans. So ocean is deep, has high heat capacity, and it takes up 93% of the excess energy from global warming, and so the energy into the ocean has to come by reduced evaporation, because otherwise ocean would be cooling and it would be giving energy back to the atmosphere. A slower response dependent on the changes in the ocean surface temperature that are a result of a response toward a new equilibrium temperature set by the radiative forcing and atmospheric feedback. So this is the net slower response that is going to give you, on scale of years to decades, the net change resulting from the radiative perturbation. Of course, we are in a transient situation now where the perturbation to the radiation is changing continuously because greenhouse gases are increasing continuously. Of course, there's contribution from land as well. But the fast adjustments also include the fast land response, but typically the atmosphere response, including the land response, go into the fast adjustments to radiative forcings. And the question is the net precipitation change from fast and slower responses over a longer period determine the shifts in the precipitations, changes in the amounts, and so on. And just like there is a climate sensitivity, in case you don't know what that is, you can look up other podcasts on my courses. But essentially, we double the atmospheric CO2 and keep it constant and see how much the temperature change that will result when we reach equilibrium. So that's called climate sensitivity, and the models produce different climate sensitivities. It's not so easy to derive that from observations, and there is evidence that it's not stationary if you go back to the ice ages versus the present conditions. For example, climate sensitivity is not necessarily the same. So in this case, we are looking for the hydrologic sensitivity of how much precipitation would result from per Kelvin warming, let's say. Okay, and to look at the lapse rate response, which is part of the stability that we are mentioning here, the atmospheric stability that we are mentioning here, we can simply understand it in terms of this. So you have the lapse rate that we know up to the tropopause in the unperturbed profile. And if we have a perturbation of delta Q, radiative forcing, if there is no lapse rate feedback, then you would just shift the lapse rate so that the atmosphere would remain in balance. So uniform temperature changes happen over the vertical. Whereas if you have a negative lapse rate feedback, then the surface warming is less than the warming at the upper atmosphere. So larger temperature changes in the upper troposphere happen, which means the outgoing long wave radiation is larger now at this temperature. So essentially you're going to have a negative lapse rate feedback to the radiative forcing of delta Q, whereas the positive lapse rate feedback would give you a greater warming at the surface and lower warming at the upper atmosphere, so that the outgoing long wave radiation is reduced and the initial radiative forcing is reinforced or amplified. There is some evidence that there is a let's see, this feedback is dependent on latitudes. So in the lower latitudes, you typically have tropics, you have typically negative lapse rate feedbacks, whereas at high latitudes you get a positive lapse rate feedback. Obviously these have consequences on how things respond, not only in hydrologic cycle but also the warming patterns like polar amplification, for example. Okay, so here is a nice schematic from this paper which looked at the precipitation response in more detail. So in the unperturbed situation, we have a balance. So you have top of the atmosphere long wave going out, balancing the incoming short wave and the outgoing short wave. So that's the albedo effect there. So what reaches the surface and what's reflected from the surface versus what's reflected at the top of the atmosphere, downward long wave at the surface and upward long wave at the surface. And there are also, of course, sensible and latent heat fluxes. And again, we look at the perturbation to the precipitation would result from radiative forcing. As we said before, Q is the net radiative forcing minus sensible heat coming from the surface, which is equal to short wave perturbation plus long wave perturbation minus the sensible heat flux coming into the atmosphere from below. Okay, so the fast or instantaneous response, actually here timescales are split into an instantaneous response where you have delta Q producing a precipitation with atmospheric circulation changes, land response corresponding to a change in delta Q. So you see the perturbation in precipitation here, delta P, and the rapid adjustments then produce water vapor response, temperature response in the atmosphere and land, and cloud response. Okay, and there is an associated lapse rate change shown here, which is implying a negative feedback because you have slower warming here than in the upper atmosphere, less warming here than the upper atmosphere, so you have some perturbation to the precipitation. And the longer term feedbacks, years to decades, so here they are separating the instantaneous from years, and the equilibrium kind of time scale, decadal time scale, assuming you apply a perturbation and just keep it, or you apply a perturbation and then it's gone, right? So here you have not only water vapor, temperature, and clouds, but you also have adjustment to the net balance. So you have delta F now. So here you have a loss, increased loss here, and this is the second contribution to that, and here delta F goes to 0 because the whole system is adjusted with this red dashed line showing the new lapse rate with all the precipitation changes from fast and slow time scales. So models indicate that the fast precipitation changes with absorbed atmospheric radiation, increasing watts per meter squared here, is negative. So precipitation change here is negative in terms of percentages with increased atmospheric absorption. So that's the stabilization effect that we mentioned. So you can see here that the forcings included in this so-called precipitation driver response model intercomparison does CO2 doubling, methane from anthropogenic forcing, methane tripled, solar radiation, so solar activities, sulfates, black carbon, and so on, ozone, and so on. And there are two other models included here from Andrews and Kvalewag. I don't know how it's pronounced, sorry. But the main point here is that this is frustrating. This HP that I bought is fairly new, but somehow its sensitivity to mouse is changing. Nonetheless, the various forcings produce different sensitivities both in the fast and slow precipitation responses, but this is positive. So with surface temperature change, that's the slow change, right? Ocean takes up the heat with its low heat capacity and deeper depths and slow time scales compared to the atmosphere and land, and over time it produces the slow response, net climate response, which is positive here, whereas the rapid response is negative. So the net response over time is going to be a combination of the fast response and the slow response. And what we want to do is here go to precipitation extremes, right? So it turns out that the total precipitation change includes these time scales, and then we need additional theories to explain extreme precipitations, and it turns out that it tends to scale closer to the Clausius-Clapeyron relation, where Clausius-Clapeyron says 1 degree warming is going to give us 7% increase in humidity. Then the precipitation change is typically less than that, 2 to 3%, which has implications for vertical fluxes, because if you are loading the atmosphere at 7% with humidity but only raining out 2 to 3%, then the vertical fluxes change and the circulation changes and so on. But extreme precipitations can scale much higher than the 2 to 3% change in precipitation. Okay, there is vast literature on this. This is a very deep, extensive topic, and there are model biases we have to deal with as well along the way, but you should definitely read up the key papers like the Bryan and Soden, the Sandrine Boni et al. In terms of robust responses, Paul O'Gorman's extremes arguments that we will look at, and so on. Okay, so I will leave it here, but this is just a brief introduction to constraining global or regional precipitation changes in response to radiative perturbations, which is corresponding, of course, to the global warming that we are interested in. Okay.